last half of this chapter, which is chapter 6 in EE211. So the last part of this chapter 6 on capacitors and inductors in the DC world, we will look at applications. So first, probably haven't figured it out yet, but you will soon enough, is that any circuit that you put a capacitor in, you could put an inductor in and do the same kind of a function with an inductor instead. But we end up using capacitors for a lot of electronic applications because the capacitors are smaller and they are a lot easier, cheaper to manufacture in large amounts. So they end up being used a lot more in circuits than do inductors, with a few exceptions. In particular, inductors are used exclusively for relays, delay circuits, and some sensing devices, telephone circuits, power supplies. All you have to do is open up any power supply and you'll see some transformers and inductors in there, partly because of their current carrying capability. Electric motors, microphones, and loudspeakers all use exclusively inductors, and whereas capacitors are much more likely to be used in electronics because they are small and cheap to make. But both capacitors and inductors are frequency sensitive. When we start the AC circuits, you'll see how that affects everything. So let's look at two really important applications of a capacitor in with a resistor, which we're going to formalize some of this resistor capacitor circuits in the next chapter. But right now we have two applications that we can look at, and those are differentiators and integrators. So we'll look at the integrator circuit first. It's an op-amp circuit, and just as the name implies, what an integrating circuit does is take the voltage on the input, whatever that may be, and integrate it. So for an integrator, you have what looks like an inverting amplifier configuration, but the feedback resistor is replaced with a capacitor. So now all we have left to do is analyze this circuit, and although your book has it in it, I'm going to go ahead and do this problem by hand, just because I think it's useful to do it that way. So remember, if we have an op-amp circuit, that one of the assumptions that we make is that no current is going into either one of these terminals, and that the voltage that we have right here is the same as the voltage that we have right here. So this voltage on this node, and it's the same thing when we have a capacitor in the circuit. So the voltage that's at that node is the same as the voltage that's at that node, and this non-inverting node has 0 volts in, it's tied to ground. Therefore, the voltage at node A is also at 0 volts. And no current is going into this terminal right here. So using Kirchhoff's current law and applying our rules of op-amps, we have that the current going into node A equals the current going out of node A. So I through the resistor equals I through the capacitor leg of this circuit. Current in equals current out, which is a direct application of KCL using our op-amp rules assumption. So we can get I in the capacitor, or in the resistor, that's the input voltage V1 minus VA over R. And we can also get the current in the capacitor, which is C voltage in the capacitor. Let's make sure we have this convention correct. So by our convention, this is voltage 1 minus voltage out is down here. Voltage A minus voltage out is the voltage in the capacitor. But we know that this is 0 minus voltage out right here. So that makes this sign be negative right here. So V out dt. So we have those equations now. I hope you, so it's really 0 minus C dV out dt. So 0 minus makes this part be a minus sign, and VA is 0 volts right here. So we have V1 over R equals minus C dV out dt. So this looks like a differential equation that we can solve. So we do V1 over R dt, we'll put the minus c on the bottom over here, equals dv out. Correct? I'm missing something. No, I'm not. That's all good. We're all good. Yes. So, which is exactly, looks like the equation in your book, 6.33. And so if we integrate both sides now, we will go ahead and integrate both sides. Where's my pen? So I'm integrating that side, integrating that side. So I can move this constant outside, which we will do. Where's my pen? Can't find my pen. So I have my 1 over RC integral of V in dt equals integral of dv out, which if we do that, we now have minus 1 over RC integral V1 dt equals V out. And we're integrating from 0 to t on both sides. 0 to t equals V out at t, because remember there's implied a 1 there, there's nothing else there. So V out at t minus V out at 0. And if we assume that the capacitor was initially discharged, which is a fair assumption in most cases, we get V out of t equals minus 1 over RC integral from 0 to t of the input, V1 of t dt. So this indeed shows that within a proportional constant that's related to the R and the C multiplied together, that the V out will be the integral of the input voltage. The differentiator circuit also uses the inverting op-amp configuration, but instead has the capacitor on the input instead of the feedback position around the op-amp. But once again, we apply the same rules to analyze that circuit, and when we do, we will come up, pause here. When we do apply the same rules for op amps, current in equals current out, apply KCL, and we will get V out is inverted of the V in, but it's inverted of the rate of change of, actually it's the rate of change of the input. So we differentiate the input voltage times, and it's inverted because it's in an inverting configuration. So V out is proportional to the derivative of the input voltage. So I'm going to show you here a couple of examples separate from the book. So I'm going to do an example that's an integrator. R is 100k ohms or 100,000 ohms. C is 47 microfarads, so there it is in farads. And my input voltage is a cosine, so it's 10 cosine 2t, and t is time. Input voltage is a function of time, and this is an integrator. So I'll apply the equation that we just developed on the previous sides, and I know that V out will be minus 1 over RC integral from 0 to t of V in plus any initial voltage that exists, which there is no initial voltage on the capacitor. That should be, yeah, well, that's V out, that's on the capacitor. But we assume that our capacitor is initially discharged. So if I do that integration right there, that everybody should be able to do it, but I'll go ahead and do it. Well, some people are still reviewing calculus, so that's okay. So that will become minus 1 over 100,000 times 0.000047, yeah, that was 47 microfarads, times, and now I'll just pull out the 10 because 10 is a constant right there, so it isn't involved in the integration. And so if we remember integral of cosine of something, well, derivative of a sine is cosine, so integral of the cosine must be the sine. So I want to integrate that part. So if I integrate, I have to look at the argument here of this cosine function, which would be, let me get rid of that little mark I accidentally made there. There's my little eraser. Okay, so this would be times 1/2 times sine of 2t. Because if we differentiate sine of, we're integrating cosine 2t, and so this is the answer. But if we differentiate that, it would be derivative of the sine is cosine times the derivative of this, which would be 2, and we have to have that be canceled out so that these two equate to each other, the integral and the derivative. So that's the integrated form. This is what V out would be. And I want to show you how to do this in MATLAB, because I know that if you all are transferring to Manoa's engineering program uses MATLAB quite a bit. Actually, a lot of engineering programs do. I actually prefer Mathematica as my math program of choice, but we'll do MATLAB too. So I want to show you how to make functions in MATLAB. So we had a first function, which was the input function right here, 10 cosine 2t, and there's a couple of ways you can do it in MATLAB. One, you can create a separate little script file that keeps your function in it, and then you can call the function. But there's a shortcut way if I'm not developing a big program, and so I can do this what's called a function handle, and I'll say V, this is my input voltage, or input input voltage function. V equals at t, so I'm going to say that the variable is t, and then here is the actual function right here. This is called a function handle, but it's defining that the variable is t, and this is the function, and this is the function's name, v. Then I just define a constant r equals 100,000, c equals 47 microfarads, and then I define my output function right here with a handle, function handle. So I say the variable is t, and there's the equation that I just did on the previous slide. And then, oh, I'm missing one line here. So just because I copied and pasted and cleared this a moment ago. Yes, I know, undefined variable s. So I just entered, let's delete all of these three here real quick. Okay, so I've entered this much of my information right now. Say enter, and then just so you get more familiar with MATLAB, this is the space I'm working in right now. But the different variables that I define end up being over here where I can look at them. So if I want to see what variables I have defined right now, I have a C. I can click on it, and I see it comes up in an Excel-like style, but I can see that there's the value of C right there. I can close that. I can see there's the value of R right now, and this one is a function handle, so you don't get to look at it quite the same, but you can see hopefully you guys can see that that the function, what I wrote for the function, is actually defined right there. So I actually had to refresh myself on plotting, so there's a help place over here, and I had to review plotting in MATLAB because I'm more a Mathematica user, but I want to plot two functions and see what they look like, see what input voltage versus output voltage looks like, and this is one of the ways I'm going to do it. I'm going to create a line graph, and I'm going to use this thing called a line space function to define my horizontal variable. So here's the format of it. So I'm going to say S is really seconds for me. S equals line space, and I'm going to define to go from time seconds equals 0 to seconds equals 5, and I'm going to do it in 100 increments. So this is going to be my time variable. And so now I look over here in my workspace and I see, I'll double click on S, and there's all of the values of S that the functions are going to use. Now the next thing with MATLAB, I want to do a plot, so I have to make the plot window open. So I'll just say figure, and I get a blank plot window. And now plot, and I'm going to plot basically X and Y twice. So I'm going to plot S, and then let me step back. I think I have to do, maybe I don't. Let's try it. Plot. There's my horizontal S, and then V evaluated at S. And then I'm going to plot S again, and V out evaluated at S. I should have called those V ins and V outs, but I think this will work. Yes. So there's my figure. So V in right here was my cosine function. V out, which is the coming off of the capacitor, you can see it is inverted from V in. It started at 0 because the initial voltage there was 0. It's not as big as the output, but this is the integrated with a constant defined by 1 over RC, integrated input cosine, which becomes an output sine. So yes, indeed it works, and that's just an introduction on how to make functions and plots in MATLAB. So there are many ways. We can do 3D plots, we can get fancy, but at least I wanted you to see how to at least initially do it one way. So let me include that in my PowerPoint real quick so that it will be saved in case you want to come back and look at it again in the future. There it is. So it would be kind of neat to, we could do a lot of different functions and look at them as well. But basically it's truly an integrator. So anyway, all right. So I could do an example of a differentiator. So if I had, for example, remember differentiation also gives you the slope of the line. Maybe I will in a future, actually we do it in the lab, so that will be fun. Okay, that concludes this chapter. There was a section on talking about, in your book there's a section talking about analog computers. The only interesting thing about this is, well, one, I have an analog computer in my lobby that you can look at, but originally op amps were developed for analog computers, and they were hardware versions of solving differential equations. The only nice thing about this part of this chapter is the reviewing of solving a second order differential equation, but we are going to see that in the next chapter anyway. Anyhow, integrators and differentiators are used for a lot of other circuits besides analog computers, so I didn't just introduce you to an archaic circuit. For example, right now a project we have on our campus involves getting very short pulses of current, and they're so short that we cannot digitize it and use it. So that pulse of current gets applied to an integrating circuit and gets spread out over time, integrating in, well, we apply integration and gain to it, and that pulse of current will get spread out over time and converted into a voltage, and then my analog to digital converter can work with it. So that's one example. It's actually a really common example of taking what an integrating circuit is often used for, taking a very short pulse and making it something that's usable for the user. Okay, that's all